Hey everyone, I guess we're about to get started. Good morning. This is an amazing turnout, 8:30 in the morning. I don't think that anyone would make it, so this is really amazing. I guess you guys do care about security. This is good. Just so you know, some of you, I saw even yesterday, downloaded my slides. I had actually updated them since several times. And the new version, or the latest version of the slides that I'll be presenting, is available at this URL, http://mrkn.co/ I guess AnDevCon. I'm also recording this entire talk, and I'll be posting the video from this afterwards, and it will be available under the same URL. Minutes to go through Android security. There may be some demos we get to do. I do encourage you to ask questions. I normally, these talks sometimes range from as short as 40 minutes to, I guess, 75 minutes. So this time around, I think we actually have time for questions. So do feel free to interrupt me if you have some specific questions you'd like me to get through. Otherwise, I also plan for having at least 5 to 10 minutes worth of time at the end for questions. So, that said, let me just introduce myself. So my name is Aleksandar Gargenta. I also go by the nickname of Saša. I've been doing Java since, I guess, long time. Mostly on the server side, actually, and then switched to Android. I've been doing Android since '98. I've been teaching Android, actually, since 2009. I'm somewhat local. I live in Walnut Creek, but I actually run an Android user group here in San Francisco, well, north of here. I also run the Java user group. In fact, we have an event tonight, which I invite you to attend, sfjava.org. I also work at a company called Marakana. We focus on open source, or training on open source software, so hence I've been exposed to Android quite a bit through my work. That said, this talk is on Android security, kind of all-encompassing from what we as developers need to do, what the platform is doing or could be doing better, what the users potentially need to worry about. So we're going to attack it from the different angles. So we're going to go through the security model, the permissions on Android, how they work, encryption, device admin. I'm sure hopefully some of these things ring a bell. The routing and kind of what that entails. Why is it done? How is it done? Why shouldn't it be done? Anti-routing, so what are the things that we could do if we were platform developers to prevent routing or try to mitigate it? Tab jacking, what are some of the issues that you should know of as developers? Some of the best practices, and then some of the other concerns. That's a general idea for this talk. So why care? Okay, I guess, let's set up the motivation for this. So ultimately, Android has grown to, latest statistics are going to put it somewhere at 1 million activations a day. It hasn't reached that point yet, probably, but it will soon enough. And so, as you could imagine, the more important and more, prevalent a platform is, the more interest there will be in the hacker community, the not so good hacker community, to try to take advantage of users running these devices, whether for just monetary gain or corporate espionage or some other reasons. Also, what we may not realize is that Android is also heavily used in enterprise. So it has access to corporate data, but also it's modified and customized for specific enterprise applications, whether it's specific tablets or set-top boxes, or even in areas like cars and flights, like on flights, for example, in planes, you can have Android potentially powering your infotainment center. So, of course, in all those different areas, security is important to the degree that enterprises are really paying attention to these sorts of security threats. And this is just a list that I compiled a month ago. If you just go Google Android security, I'm pretty sure you'll find other things that should be on this list. But this is all I could fit on one slide, including my little pretty graphic. So what are the foundations of Android security? So it comes down to the different aspects that platform provides to us, the developers, but also us, the users, in order to provide us with as secure environment as possible. Of course, without impacting the user experience to a large degree. So what we're going to discuss essentially are things like application isolation, so permission control. I'm pretty sure you guys have heard of permissions, so to what extent you've actually been able to take advantage of them, that's something we'll see. So we want to discuss how, why is it that applications cannot, go and damage the rest of our system? What are the sorts of bounds and checks that are in there? How can we prevent misbehaving, apps from affecting, us, the user, or the system, or other apps? Application provenance. So we'll talk about, idea of trust. Can we trust the author of the app? Can we make our apps be more tamper resistant? Data encryption, or better yet, just how do we, take care of our data? How do we make sure our data is essentially kept safe? And then access control as a way of, what are the sorts of things that Andrew has in place that, help essentially control access to the physical access to the device. And of course, there's going to be some other security-related concerns that we discuss. So before we go into these details, though, one thing I like to do is just go over the stack. Now, how many of you have seen this picture before? Okay, so that's awesome. So at least I would say about a half. So what this is, essentially this captures my version of it. I mean, there are a zillion different versions of the same picture. And what an Android OS really looks like, right? At the very bottom, we have the Linux kernel, which is modified for Android. It's Android, one thing I want to make clear is that Android is not a Linux operating system the way we think of our Linux operating systems. It doesn't have password file, at least not the way we envision it. Doesn't have su command, at least not by default. Doesn't have a lot of x11 or glibs or other sorts of things that we kind of come to assume are part of standard Linux distributions. So what's the purpose of the Linux kernel? It is mostly there for several things, several reasons. One is to provide isolation from app to app, so to enforce, if you will, the security model that we'll talk about next. And then of course the other is to provide a driver model and a huge assortment of existing drivers that have been already written for Linux, and things like threading, CPU scheduling, memory management, that sort of thing, right? So that's what the Linux kernel is doing at the very bottom. We have this native layer, which itself is kind of composed out of multiple layers, like the Bionic library that you might have heard of, which is the equivalent of libc, the native daemons that essentially provide services, some of which run as root, and that's the sort of thing that we worry about. The HAL, the user space hardware abstraction layer, that essentially abstracts away the device drivers from the rest of the platform, makes porting a heck of a lot easier. Then native libraries, like for example, libwebcore, which is equivalent of WebKit, which was at one point hacked on Android, for example. SQLite, OpenSSL, even things like media framework like Stagefright and so on and so on. Like the packet videos OpenCore, which was also a source of some of the security issues in the past. So there's a lot of native stuff, of course, in the native layer that we come to trust. There's also this Dalvik virtual machine on top of most of our apps run, right? Some of you may be writing apps natively, in which case you don't really care much about Dalvik, but most applications are in fact written to run on top of the Dalvik virtual machine. You'll come to see that Dalvik is actually great in that it doesn't play a role in the Android security. Okay, it's left up to the Linux kernel to take care of it. The application framework is where our services live, or our platform services live, like location manager, vibrator, sensor manager, and so on and so on. So these are the things that essentially give us, the developers, access to the lower levels of the platform. And then, of course, at the very top are our applications that take advantage of not only the application framework services, but also potentially of components of other applications. And this is important because even those applications at the very top become part of the stack. So they become part of the APIs. So the first thing we want to discuss is this idea of application isolation. So if any of you did ADB shell to an Android device or an Android emulator, you would have seen essentially something that looked like this. Of course, you wouldn't necessarily see the kernel. You would assume that it's there. But essentially, you would see a bunch of, if you type PS, of course, a bunch of processes. So you may encounter a process called vol-d, netd, install-d, and you may notice that those actually run as root. So something we'll come back to later on. You may notice there's something called service manager, also runs as root. It's kind of important for discovery of services. Zygote, which is this kind of half-baked Dalvik virtual machine that gets forked into our, essentially, Dalvik virtual machines that power our devices or our apps. The system server, which is the home for all of the system services, so all that application framework services like location service and whatnot, activity manager service, package manager service, that's where they live. And then at the far right, you see our apps, right? Notice how our apps are essentially a stack on their own, right? They are, each and every app runs in a separate process. So they don't share any memory, they don't share any resources. Of course, they share the underlying resources, but they don't directly share anything, whether the file system, so they don't have access to the same files, excluding the SD card, and they don't really have access to each other's files, and they don't have direct access to each other's components. They can talk to each other through different means, we'll talk about it in a moment, but they basically don't really have anything in common, and this is important. It's the Linux kernel that provides isolation, because each and every app runs in a separate process. The process management is essentially the job of the Linux kernel. And notice, of course, one other thing I wanted to mention is that each app has a Dalvik virtual machine of its own. So this is actually very interesting and important for Android. So by default, at the time of the installation, each app is assigned a unique user ID. And anytime it is started, whichever component of the app is started, it is run in a separate process. Now, it is possible for multiple apps to share the same process and or user ID, but only if they're signed with the same, essentially, key. So if they share the same public certificate embedded in the app, then they can essentially take advantage of it. It's not a very common use case, though. What's really, really important and good about this is that this isolation is based on essentially decades-old Unix security model. So this is not Android trying to essentially build something from scratch and hope that it works, but rather they're basically riding on top of something that's been out there for years and years and something that we can trust. The application framework, as we saw, the system server, also runs in a separate process and not as root at that. So that's something we'll discuss as well. So on Android, the Linux kernel, as I mentioned before, is the sole mechanism of essentially enforcement of this of application isolation. And the Dalvik virtual machine plays no role. And this is important because back in the Java ME model, I don't know how many of you have done work on J2ME, where multiple apps share the same virtual machine. It was the virtual machine that essentially had a security manager in place, and its job was to essentially ensure that apps don't step over each other's bounds. But that meant that apps were no longer able to talk to native libraries. They couldn't take advantage of anything beyond what was in essentially the profile of that particular device. There was no mechanism for them to escape the sandbox of the security manager. And so that essentially led to crap experience. I mean, J2ME apps were never considered first-class citizens on any of the devices that essentially powered them. And so, we wanted something different. So the Android team decided to make Dalvik essentially oblivious to this whole idea of security. So now the native code, as well as Java code, or Dalvik code, at runtime, is subject to exactly the same security restrictions. There's no benefits, no advantages from the security point of view from writing code natively or in Java. Yet you get to take advantage essentially of all the platform features should you want to, if you want to essentially drop down to a native level. And again, same rules apply even to system apps. So this is not, this idea of app isolation doesn't just apply to third-party apps or our apps, but also applies to the built-in apps. There's some minor differences in what the system apps can do that we cannot take advantage of, but for the most part, the rules are pretty much the same. Now, this is kind of what you end up with. This is a default scenario, right? So if we had some app, call it app 1, that wanted to talk to native daemons, they wanted to talk to the other apps, they wanted to talk to Zygote or system services. By default, for the most part, the answer is no. So by default, each and every app is essentially not able to escape its own sandbox. So no app can essentially do anything that will overtly affect the system, affect other apps, or affect the user. So for example, you cannot take advantage of APIs that cost user money unless the user has given explicit permission to do so. You cannot, for example, shut down other apps. You cannot vibrate the device. You cannot keep the device awake. Things that essentially would affect the usability of the device or other apps is explicitly forbidden unless the user or the app has been essentially granted a permission to do so. So how do we get there? How do we escape the sandbox? So basically what we do as Android developers is we declare that our apps use permissions. By adding, as you will see in a moment, a uses permission essentially element to our manifest file, we are asking the end user to grant us permission for us to make use of the restricted API. Okay? If we don't do that, if we don't actually add this uses permission and we're not essentially granted that permission, we can still make invocations of the API, but those invocations will fail at runtime. Right? So essentially we'll end up most likely with a security exception. Now, one thing I wanted to mention is that apps can in fact talk to each other through intents. Some of you are probably, hopefully a lot of you here are Android developers, so you've started one activity can, for example, start another activity, and it does so through intent, so you can pass it data through intent. So they can essentially talk to each other through intents. They can also talk to each other through binder, which is the Android's IPC mechanism. Okay? And this doesn't require any permissions by default. And of course, they can exchange data through content providers. This is actually interesting because one of the things that becomes somewhat of a problem with Android is how do we know if two different apps are in fact talking to each other? Okay? And does that affect us or the security of our device? So we'll come back to that point in a moment. Now, as far as the built-in permissions, the list is huge. I mean, this is just to give you an idea for some of you that have not worked with permissions extensively. So access the file location, access Wi-Fi, use the call phone, use camera, access the logging, it's a read from logs, for example. Use wake logs to keep the device awake. Vibrate, write contact, send SMS, receive SMS. These are the sorts of things that we would need permission for. For the full list, you can of course go to this URL down at the bottom and you'll see it to see the list. Now, one thing I wanted to make clear is that not all the permissions that are on this list or on the list below in the URL are actually accessible to us. Some of these permissions, like for example, install packages, we cannot use. And I'll explain later on why. So the fact they're listed there doesn't mean that they're necessarily something we can take advantage of. So, for example, let's say you were building some sort of an app that vibrates anytime you come close to, I don't know, one of your buddies, right? So the app would need access to your current location. It would need access to the internet in order to basically, provide this, or register your location in some central server, and that central server uses its broadcast mechanism to other friends of yours to tell them where they are, like the latitude. So what you would need, essentially, are permissions to access the defined location. That's how you essentially get access to GPS. Access or Android permission internet, which essentially enables you to talk to or take advantage of the TCP/IP stack. And then vibrate permission if you want to be able to actually vibrate the phone, I don't know, when you approach somebody of yours, okay? Or come close, whatever close may mean. So this is the syntax, and I'm hoping that at least some of you here have used this in the past. In fact, you cannot really get very far these days without using permissions. Now, how are the permissions generally enforced by the system? So this is essentially how most services work on Android, right? Let's assume we have some sort of a device over here. We can call it, dev foo. Imagine it's some important device like a scanner, a camera, something that we care about, right? We could potentially, write an application that would try to directly go over here and use that device, right? But that's generally hard. So instead, what we typically have on Android systems is we have this HAL idea of a HAL model, which is essentially a hardware abstraction model, right? So what we do is or what the device manufacturers do, or OEMs, they provide us with something called libfoo. Generally, let's assume that's what it's called. That essentially is user space library, shared library, that knows how to talk to the driver. Okay, we could load it, right? We could actually load that library and try to access HAL. Now, this library is written in C. We may prefer to code in Java. So what the OEM may also do is provide us with some sort of a JNI bridge or wrapper. So think of it as some sort of a foo native. It's a Java class that essentially defines some native methods, and those native methods are implemented through, say, something called libfoo JNI. And we could load both this and this into essentially our process. And we could try to use it, right? Nice, clean, easy to use APIs. But where we would generally fail is right here when we basically try to open up this driver. The driver itself tends to be protected through simple file system permissions. So the point being is that the libraries are not, they don't have to be essentially security aware. These libraries, all this stuff, essentially doesn't care about security, nor does Dalvik. It's really whether or not we have physical access to the file, in this case, the driver. So what we do instead, and what Android does instead, is that most of these services, right, most of these, say, call it drivers, in Android, happen to have basically some sort of a service that is persistent and it's stored or loaded into the system server. The system server, don't forget, is the home for all of the system services. And this, call it foo service, would register itself with that service manager, right? I don't know if you remember, which is another daemon that sits there in the background, runs at all times. Okay? So what is the purpose of the foo service? Well, of course, on top of being able to kind of aggregate or provide a stateful access to the underlying hardware and provide some additional potentially value add on top of it. One of the big jobs of the foo service is to also essentially right here at the point of somebody trying to use it, so think of it kind of right here, do a permission check. How does it do a permission check? Well, when we want to use the service, we don't actually access the service directly. Instead, we use something called foo manager, right? So what do I mean by this? If any of you have used, let's say, the location service, right? You actually don't get access to the location service. What you do, you get access when you go systems or get system service and you say location, what you get back is something called location manager. Location manager is essentially a client-side component. It runs in your virtual machine, in your Dalvik virtual machine. And the whole purpose of the location manager is to essentially bridge to the service, to essentially hide the fact that you are talking to the service in another process, to abstract this idea of IPC, the inter-process communication, away from you, right? So you think you're talking to some service somewhere, you're really talking to a local manager, which is then bridging or proxying your request to the service. Now, what's going on in addition to this is when we actually make this call, we don't actually make the call directly. Instead, we actually talk through something called binder. So we kind of go like this. Binder is a kernel driver that, among other, its job is to provide this, IPC bus. But in addition to that, it actually also provides the information about the caller to the callee. Okay? So the callee, being the service, knows now about the UID and the PID of the calling process. So what is the purpose of that? Well, once we have that information, the service can actually go to the package manager, or package manager service as it's called, and say, hey, for this UID and PID, does the calling process have a particular permission, like access final location, or vibrate the device? And at that point, it gets yay or nay, either does or it doesn't, and then it decides what to do. And most likely, if you don't actually have the required permission, essentially you end up with a security exception. Okay? So this is how most, not all, but a large percentage of the services in Android, or I should say restricted APIs in Android, are enforced. Through this idea of services wrapping essentially these native libraries, and then also, in addition to that, providing this essentially security check before we can get access to them. Okay? In fact, if you kind of want to take a look at it, just using vibrator as an example, if I were to do an LS of the vibrator driver, you will notice that it is owned by system, and you'll notice that only the system user can write to this driver. Okay? So that means that our apps, if you remember the previous slide or a couple slides back, we don't run with system user. So therefore, if we try to write to this driver in order to tell it to vibrate the device, good luck, it won't happen. So what do? We then use something called vibrator instead of vibrator manager. For some reason they call it vibrator. And vibrator is really just nothing more than a client to this thing vibrator service. What does the vibrator service do? Well, let's take a look at it. The actual method, vibrate method that we invoke to vibrate the device, the very first thing that it does, it goes to its own internal context and says, hey, check the calling or self-permission, and essentially says, does the calling process have the permission vibrate? If it's not been granted, so if it hasn't been granted, we then end up with essentially over here, as you can see, the security exception. Okay? And that's how most of the services are enforced, essentially, the security concerns. Okay? Now, kernel permission enforcement. Okay? So what we already know that kernel contributes to the isolation of apps. We also know that the kernel helps enforce essentially or prevent us from directly accessing most of the drivers. But there's more to this. So kernel in some areas plays a more direct role. So for example, for internet, like how do we actually get access to the internet? Well, it just so happens that the Android's kernel, it's been modified with something called paranoid network security. Okay, so what is that? Essentially, it's a little, think of it as an if statement around the TCP, well, the IP stack, right, the network stack, that says, does the calling process belong to group 3003? Why that group? That's something that they came up with. Okay, they call it the INET group. Okay, if it doesn't, if the process does not belong to that group, it doesn't get access to the internet. Okay, it fails. So how do we actually then get access to the internet? Well, we use remember the Android permission internet over here? That's what we use. What does that give us? That gives us essentially access to the INET group, which itself is mapped to that 3003, group ID. So we essentially, by using a permission, at runtime we get this group membership, and then the kernel does the enforcement of whether we belong to this group or not. So essentially our logical permission becomes a specific group ID at runtime. Okay? Another way to enforce it is through essentially more of file permissions. So for example, camera or read logs or write to external storage. The way these things work is that these again are mapped to specific group IDs. And by being mapped to specific group IDs, that gives us write access, or in some cases read access, of those specific drivers. For the most part, we're talking about drivers. So in some cases, we do directly talk to drivers. We don't go through these system services. We don't go this roundabout way through IPC. We can talk to them directly. But again, for us to be able to do that, we need access to, or we need an appropriate permission. The permissions are granted to us by the virtue of mapping logical permissions to group IDs. Okay? Permission granting. Okay? So now that we know that our apps are subject to these restrictions, and we need permissions in order to access the restricted APIs, how do we get there? Well, the permissions are granted once at the app installation time. Okay? And this is very interesting for Android. So this is not like Microsoft Vista, where you're constantly being nagged to approve of whether you want to do the next thing. It's essentially at the time of the installation, you as the end user either grant the permissions or you don't grant the permissions. If you don't grant the permissions, the app doesn't get installed. There's no provision for you to dynamically later on grant or ungrant permissions, and there's no provision for you to partially grant permissions. It's all or nothing, whether you like it or not. There's some exceptions to that. Basically, URI permissions are kind of like passed from an application to application. But that's, and USB permissions, or in essentially API 12, there was Android added support for the USB, accessing USB devices, and also for accessories, for accessory API. And essentially for that, you need these USB permissions. They're kind of granted dynamically. But that's an exception. It's really they're granted statically. Now, the question, though, becomes can a any user essentially make intelligent decision as to whether the collection of all these permissions they're granting is safe or not. So essentially Google's or Android team's objective was more power to the user. Let's give the user all the power in the world. Let's have the end user decide on what they want to run and what they're comfortable with or not comfortable with. But most users, it turns out, are not very well equipped to deal with this. So what do? They basically are conditioned to say yes, yes, yes for the most part. Not you guys, but a lot of users out there. So another little feature of Android is that certain permissions, like wake up on boot, are not considered dangerous enough. So the user, in order for the user to grant these permissions, they actually have to click on this thing called See All, and then they'll see that they're actually, in addition to all the other dangerous permissions, granting those as well. The one thing that's somewhat kind of scary is this idea of combo permissions. So for example, let's say we have two applications that we install on a device. One that essentially, let's say wants access to our email, so you can maybe has some this super duper, voice search for email, and we granted access to our email. And then we have this game that wants access to the internet because, these days everything is ad supported, so it needs to talk to its ad servers, right? So we say fine. But what we don't know is that these two apps can in fact talk to each other. Right? They can discover each other, they can exchange data with each other, and so the app that has access to read your email, that app can leech that email and essentially send it to the app that has access to the internet, and then the app can send your email out, to whatever, your competitor or who knows where. So the point is, we may think of these apps as being isolated from one another, but we don't know whether and if they do take advantage of the Android's IPC mechanism to essentially circumvent that fact. And this is what a grant screen looks like. Okay, so granting permissions. Now, the question though becomes is what are the alternatives? So do we dynamically grant permissions every time an app starts? Do we grant permissions on use? Well, Google's or Android's team essentially perspective on that is that it's annoying. If we were to implement that approach. It's hard to provide seamless app switching. One of the real cool features of Android is that you go from app to app to app without really thinking. It's called a user task. It's what you want to do. It's about the user. It's not about applications. But if now you were constantly nagged to approve of specific permissions of when going from app to app, that would essentially break that illusion that you're essentially just using whatever the system has and not specifically focusing on a particular app. And of course, the other problem is that over-prompting the user leads to essentially, conditioned response. They just say yes, 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 like people, ended up doing on Vista, and does that really lead to good security? And of course, if the user is already committed to the app on the time of installation, they may use half of the app, provide all this personal info, and then all of a sudden they see the app wants permission for something they don't like. Well, at that point, they may grant it, even though, if they were prompted for the same thing and install time, they may not. So the other problem with respect to uninformed, are users well equipped to know what to grant, what not to grant? Well, Google's response is, well, let app ratings and comments from the more sophisticated users influence more novices users' decisions as to what to install, what not to install. The only problem with that is that users then become like sheep. They basically just look at that number of installs, essentially figure, and then go by that. Like if it's a large number, then it's fine. Otherwise, who knows, right? But in the past, there were in fact apps like live wallpapers that essentially had compromises in them or had security exploits where they were leaking information from your device to some servers in who knows where, some say competitor countries, and the app looked cool, and most people just yes, installed it, and enough people installed it initially that other people just came later, and there's like, oh, 200 installs or 200,000 installs, this must be safe, let me go and install it as well, right? So at least one good feature of the Android market, or at least the Android distribution mechanism for apps, is that Google does have ability to pull apps. So essentially has a remote kill ability to pull apps off of your devices if they're found to be malicious in nature. But it's more reactive than proactive, right? You're still, you're the one who's ultimately responsible for what goes onto your device. Now, application provenance. So this is a term that I guess I saw in one of the semantic reports on Android security, which you should read if you care about security on Android. Can we trust that the author of the application is really who they say they are? That's really the question we want to answer, especially on the first install. So that's something we need to discuss. Can we trust that our apps are tamper resistant, so that they cannot be changed once they're installed? And so one of the ways Android tries to deal with this is that developers are required to sign up for a developer account with a valid credit card, which is then tied to their account. And so if the developers are found to be malicious, right, Google can go after them. So the idea is, as you will see, that Android requires apps to be signed, and the idea is that through this idea, through the signatures, this trust that exists between developers and Google can then be passed on to you. So then now if you trust Google, then hopefully you can also trust these developers. One thing to note, though, is that applications can be installed through alternative means. Like they don't have to be installed through Google Market. They can be side-loaded or come from other app markets as well. So how does this self-signing thing work? So I already mentioned all apps have to be signed. So this is not up to us. So some of you might have just done a hello world and you click the run application and you see it works, but you haven't done any signing. So you're like, well, what's signing? Well, if you try to upload an app to market, you actually are required to first sign this app with something other than the debug key. So the signatures are based on this public-private encryption algorithm, where basically you have a private key that is used to digitally sign the app, and then the public key in form of a certificate, and the signatures of the app resources are bundled together in the app's APK. Okay? The question is, what is this good for? Right? Why the heck do we need signing? Well, I already mentioned the idea is for this, for the trust that exists between Google and the developers to be passed on to us. Well, unfortunately, the issue is that these certificates that are embedded in these applications can, and in fact are encouraged to be self-signed. What does that mean? Essentially, the private key that is used to generate the signatures is also used to sign the public key to generate a certificate. Right? And this is great from the point of view that you don't have to go to VeriSign or something like that to essentially pay however many hundreds of dollars to essentially get a stamp of approval that you're legitimate. But it also creates a problem in that we don't really know that what we're getting has really come from a particular developer. Since the keys can be self-signed, there's no one to vouch that there wasn't someone else who potentially stole that application, added some malicious content to it, and then re-signed it with their own key. And of course, since it can be self-signed, they can trust themselves, who wouldn't, and upload it to market. Right? So on the first install, there's really, in the current system, no real way for us to trust the author of the application. So in that regard, and especially given the fairly lax review process or non-existent review process for Android apps, which is great because it means no friction, but it's not so great with respect to security. The combination of these two things do mean that we're more exposed to essentially malicious apps than we would on other ecosystems. Now, in terms of updates, so that's where the signatures do come into play, right? So if the signature, or better yet, the certificate doesn't change from the original app to the updating app, then we can trust that they came from the same author. So in that case, it doesn't matter whether there's a CA or not. As long as they're the same, that's good. So at least for updates, okay, the signatures do play a significant role. We now know that someone can just impersonate some other author out there of a popular app and essentially have their app replace our legitimate app. And then the other reason is that it does help establish, the signatures or certificates do help establish a trust relationship between multiple apps from the same vendor. So if a single vendor actually signs multiple apps with the same private key, that means that the same certificate will be embedded in these APKs, then one of the things that these apps can take advantage of is that they can basically share UID, so they can run with the same user ID, they can actually run in the same process, and they can share signatures. So this is interesting. They can actually, they can share permissions based on signatures. So I'll come back to that idea later on. Now it is Also possible for a single APK to be signed with multiple keys, although that's not very common. Now, the other thing that I just mentioned this, the other thing that is also possible, or the other reason why we have signatures, is they help make our apps more tamper resistant. So the idea is, our apps, since they're signed, they cannot be modified by someone without breaking essentially the signature. That said, apps, due to file system permissions that we have on the device, once the app is on the device, we don't really care much about it having been signed, because if essentially someone can modify the app's components, that means they probably have root. And if they have root, then all bets are off. Who cares about signatures at that point? So this is really more important in form of distribution of apps, as they are, before they make it onto our device. You had a question?
Yeah, on the first install issue, is there a way to get, say, the public key fingerprints of the...
No, there's no. I mean, first of all, when you install, you don't see the package name. You don't really see the fingerprint of the public key. There's nothing for you as the end user that you can go on to say, hey, this actually came from a trusted source. At least not in the current market application that we have.
Why not?
Ask Google. I think they should. That's a very good idea. So that's the sort of thing that we've seen in the open source world, where they put the signatures, essentially a fingerprint of the key in in a web page, or in this case the forum, and then you can check it against some web page somewhere if you're really paranoid, and then they'll give you an idea of whether or not it's been tampered with. Yeah, exactly. So that is the problem. So one of the things we'll talk about later is, what if, for example, somebody, let's say Angry Birds, right? I go and download an Angry Birds onto a rooted phone, then extract the APK off of the rooted phone, maybe add some malicious content to it, change the name from calling Angry Birds to calling Angry Birds Burlingame, right? And then re-uploading it back to market. Will Google catch that? Most likely not. I mean, somebody else will, and soon enough the app will be pulled from market, but it may not be fast enough to prevent some users from potentially getting that app onto their system, thinking that it's the latest version of the Angry Birds app, or in this case the game. Exactly. And what do users know? Like, they can see Rovio Systems Inc. or Rovio Entertainment Inc. Well, they know that that's not the original Rovio, right? Which is the maker of the authentic Angry Birds. There's no mechanism to essentially, at least, so there are some checks and balances that Google does have in play for specifically that reason, for like some of the more popular apps. So I'm sure they do search for these sorts of things. But how and what they do is not known to us. So what I'm saying is that it's something that it's not bulletproof. I had a question. Oh, so you're asking, can you take an app, extract it, essentially change the permission? Well, so yes, except that if you are able to get the APK from your phone, that means that you have a rooted phone. If you have a rooted phone, that you can actually go directly modify the /data/system/packages.xml file and take away the permissions. The problem, though, is when that app tries to use the functionality, it will fail with a security exception. It will not expect it, so it will crash and burn. Now, that is actually a good point. Like, for example, one point, Angry Birds required send SMS permission, and people were like, what? Why the heck would this need it? But it turned out that in some European countries, they used the send SMS to pay for premium content, to download more content into Angry Birds. But to us here, that made no sense. Thankfully, in that case, the actual online comments and feedback, did help persuade Rovio into taking that away and re-uploading the app. Right. So anytime an app is updated, if the permissions modify, whether they're added or removed, essentially Android requires the user to approve essentially the update. And that's even if you have that automatic updates enabled, you will get prompted. It'll say manual update required. It will not do an automatic update whenever you change permissions. Okay? So let's move on. Thanks for all the questions, but let's actually try to move a few slides forward, and then we'll hopefully get to more questions. So this idea of signing, there's some problems with it, right? So what if you lose your key, or if your keys expires for whatever reason? You didn't read the docs that said your key should be valid for at least 25 years. Well, there's no real way to update your apps then. So that sucks. You end up having to essentially issue a new app. So your app will not be able to read the previous app's data. So you'll end up having two apps in the system. Okay? So don't ever lose your private key, and don't have it expire. Now, if your key does expire, the app will still continue to work. It's already installed, but you will not be able to update it. If your key is stolen, there's no real way to revoke the key. Okay? I mean, you can go talk to Google, but there's no official mechanism for you to do that. So that's also a problem. And like I mentioned, how do we trust the author on the first install? Is this a real author? Is this an imposter? How can we get access to the cert? Can we check the cert? Has this app been vetted? Do we know if someone actually reviewed this app that it contains some malicious data or content? Should we go by the number of installs, which is kind of like follow the sheep? That's where those are sorts of questions you want to ask yourself. So what are the results? So the results are, these are some of the kind of essentially viruses or Trojans that have popped up in the Android ecosystem. They've been identified by the Symantec or Norton Security and also the My Lookout guys. Essentially, what these are apps that are legitimate looking apps that were downloaded, unpacked, malicious content was added to them, including additional permissions, or sometimes rootkits which actually don't require permissions. They were repackaged, re-signed, re-uploaded under a different name, or redistributed through these unofficial markets, and people essentially got them on their devices and infected their devices. So some of these things would, they range from just leaking your personal information somewhere, but they also, in some countries like Russia, what some of these applications do, they send premium SMS messages or SMS to premium numbers and essentially incur you, charges on your mobile account. So they all took advantage of the weak trust relationship. I mean, these are the steps. Like, you take an existing app, you get it, you pirate it, right? You inject malicious code, you repackage it, re-sign it, re-upload it, and then just wait for the sheep to come. Okay? Now, safeguarding our app's data. So we're now moving to the kind of the data section. So hopefully we're done with this idea of provenance, and hopefully understand that there's some real issues for, I think, Google to address in this place. So by default, because our apps have distinct user IDs, all the apps files, so all of our apps files are private by default. So they cannot be read, written, in any way, shape, or form manipulated by other apps directly, unless we specifically make the files be world readable or world writable, or if we, for example, go and put our files on the SD card. A SD card essentially is a wild, wild west. If it's there, you can assume that some other app will modify your data, and you should not trust the data there. So you should be very, very careful in how you read and parse the data. In terms of, like, if you want to make sure that doesn't get, if there's some private data you want to leak, then you may want to do encryption of the data yourself. There is, as of API 9, something called Storage Manager, which has this idea of opaque binary blobs, which allow you to essentially create these virtual file systems on the SD card, and that are automatically on the fly encrypted. At the beginning, it didn't quite work. I'm not sure actually what's the state of it today, but I know that initially when Gingerbread rolled out, that wasn't actually available for whatever. It was there, but it didn't work properly. Now, other apps, if they're signed with the same key, they can in fact get access to the same files. So you can request that they run with the same user ID, so thereby they can get access to the same files. Although that's not very common. Most of the time, if you want to share content between apps, you share it through content provider. Now, in terms of data encryption, so what do we have today? So we have VPN built in with IPsec and three triple DES and AES encryption, including certificate authentication. In Ice Cream Sandwich, Google added support for a VPN API. So essentially, custom VPN clients can be provided through essentially an app install. So you don't have to create a custom ROM just to get a VPN client that's compatible with your enterprise's VPN system. We also have 802.11, of course, that supports WPA 2 with both password as well as certificate authentication. We have OpenSSL. It's all built in. We have JCE or Java cryptography extensions, which in Android are based on something called Bouncy Castle. And this provides us with, support for all the common encryption algorithms, both public key encryption as well as symmetric encryption. As far as communication goes, the HTTP client, the Apache HTTP client is built in, supports SSL out of the box, SSL/TLS, as well as the HTTPS, the URL connection in kind of the Java's library also supports, SSL. One of the problems, though, is that the actual SSL CA store, so the store that actually where the trusted certificate authorities are stored on the device, is something that we cannot change in at least up until Gingerbread, well, including, I think, Honeycomb. That said, using encryption beyond SSL for your own reasons, like just encrypt stuff and send it over the network, is not trivial. A lot of people get it wrong. Like, for example, they don't properly use initialization vectors, which essentially it's a way of adding a little bit of randomness to the key for each message that you sign and you send over somewhere else. Because if you don't do this, if you're using the same key over and over and over again to sign different content, after a while, that key becomes weaker and weaker. It becomes easier through static analysis of the data to recover the key. So if you don't properly use initialization vectors, for example, or properly use encryption, and believe me, those encryption APIs for the most part suck, you will run into problems. One other thing is that encryption of data on the device. A lot of people get kind of confused with, or they think, well, all the data on the device has to be encrypted. Okay, fine. But if you store the encryption key on the device as well, then it's just a moot point. It doesn't buy you anything, right? Because by default, due to the isolation of the apps, the only way for some other app to get access to your data is if the device is rooted or that app has root privileges. Once it has root privileges, assume that it has access over the entire system, including the file that you use to, for example, where you store your encryption key. Right? So the only time it makes sense to really encrypt data on the device is if the encryption key is stored on some server somewhere on the device or in the user's head, never on the device as well. Right? And in Ice Cream Sandwich, they also added support for something called Keychain API that allows essentially user apps to manipulate certificates, as well, including certificate authorities. So this is something I know it's there. I don't know how it actually works. I haven't actually had a chance to play with it, of course. And then in Honeycomb, they added support for whole disk encryption. So I just mentioned this quickly. Go ahead.
Sorry, just one question. Would it be possible to create a virtual device with encryption and then mount as a disk partition?
A virtual device?
Yeah, a virtual file system, like a disk image with encryption and then mount it.
Right, that's kind of what the storage manager, the OBB, the opaque binary blobs. So that's kind of what it is. So take a look at that. So just look at the storage manager and read on opaque binary blobs. That's exactly what you're asking for. So whole disk encryption. So basically, this is something that's only available as of Honeycomb. What that is you can go to settings, location, security, encryption, and then say encrypt tablet. At some point, I guess they'll call it encrypt device. It requires that you set up an on-screen password. It doesn't work with a pattern. So the same password you use to unlock the device is also used to enable this disk encryption. It encrypts the entire data partition, everything. Okay, the entire data partition with AES 128-bit encryption. It uses basically your password is salted and digested multiple times through SHA-1, and then that's the password that's actually used to encrypt the files. There's some problems with this though. Is that the actual password that is used is directly essentially used to encrypt the files through this manipulation or through this salting. So if you want to ever change the password, you have to re-encrypt everything. Okay? They don't actually use the password to encrypt some other file that has the actual encryption password. They use the password more directly. Also, if you want to go and disable encryption, once you do this, you have to essentially master reset the entire device. Okay? This also happened to me when I tried to upgrade from 3.0 to 3.1. It required, for some stupid reason, a reset of the entire device. I was extremely unhappy. This is based on the decrypt feature of the Linux kernel, at least the kernel part. The user space binaries to manage all this are actually part of vol-d, which is a daemon in Android. They're not, essentially, they re-implemented that simply because of licensing reasons. One problem, though, is that this is not safe from the point, sorry, this is not very performant at the moment. There's no hardware acceleration here, at least that I've seen on the my Tegra 2 Samsung Galaxy Tab. Basically, read performance goes down by about 54%. Okay, once this encryption is enabled, at least for like large files. One other problem is that this is still vulnerable to so-called evil maid attack, which basically means if you ever leave your device somewhere and with someone you quote-unquote trust, if the entire boot process from the very time your CPU is powered on all the way to when your device becomes decrypted is not controlled, right? So if everything along the way is also not encrypted or authenticated, essentially someone can install a keylogger or think of it as a password logger, and thereby they can recover your password. So that's a problem. It's also prone to or subject to cold boot attacks. What does that mean? Essentially, and this sounds like science fiction, but in reality it's possible. If somebody were able to get a hold of your device when it's powered on with the password entered, even if it's locked, they could essentially turn off the device, cool down the RAM, take out the RAM from the device somehow, and I'm not saying it's easy, but it's doable, put it in some other device, boot it up, and there are utilities that will take the contents of that RAM and essentially flush it out to, say, some durable storage, right? Now you may think, well, hold on, if you take out RAM from one machine and put it in the other, doesn't all the data disappear? Well, no, actually RAMs retain some of the data for seconds to minutes depending on the temperature and other reasons. So basically, as long as the password is in memory, it's potentially recoverable. So I know this requires more considerable resources, but nevertheless it's doable. Right, so there are some, efforts to essentially only keep the password, encryption password, in CPU registers, so it never really makes its way to the RAM. That said, this is pretty, easy. We don't care about it as developers. We just assume everything's encrypted. We just, the entire data partition is encrypted, but to us, all the I/O operations remain exactly the same because the data partition is still data partition, just that it's now mounted as an encrypted device. Now, in API 11, Android also added support for DRM. I have not actually worked with it myself, but it's an API that allows OEMs, so device manufacturers, to plug in the different, essentially provide different DRM plugins. They call them, schemes, which essentially is able to authenticate and verify, the user rights to particular content. And so the idea is that your applications can interact with the DRM framework, which then itself talks to this underlying DRM infrastructure with these plugins, and through that is able to provide users access to essentially content that's digitally protected, or rights to the content that are digitally protected. So how and who uses this? I don't think that Netflix necessarily uses this, especially in the API 11 devices, because our Gingerbread devices do have it. But nevertheless, it's a step in the right direction. I haven't seen too many compromises of it, nor I have seen too many uses of it, but nevertheless, it's there, okay? Physical access control. So basically, in Android, we have the screen unlock pattern, we have the PIN, we have the password, and, with device admin, we'll talk about it, we can actually, do more. But essentially, through these mechanisms, we can at least restrict access to the device. With respect to SD card and SIM card, while we can try to restrict access to those by essentially not giving user access to the device, right, to use the device and see what's on the SD card, unfortunately, these things can always be taken out of the device. So unless they're also encrypted, and most of the time they're not, you can assume that the content on the SD card and potentially SIM card is vulnerable. Okay, so that's essentially we don't control physically anything there. Now, low-level access to SIM card is not available to apps, so this is not something that's available to apps anyways. Device admin. So, device admin is basically an idea that was added or framework, I should say, that was added to API 8, so Froyo, where basically an application can request privileges on the device that essentially make the application be a semi-administrator of the device. So what exactly is that for? Well, assume you have an enterprise that wants to enable users to bring their devices to work, their personal devices to work. And the users then want to be able to use their devices to access corporate data. Well, the enterprise may say, sure, we'll give you access to the corporate data, but in return, we want control over your phone. So what they do is they essentially provide you with an app. That app requests essentially to become a device administrator. So you ask the system or the user to become a device administrator. And if the user says yes, the app now is able to do things like wipe the device, or lock the device, require that the device lock password be set, monitor device unlock attempts, and for example, if there are too many attempts, unlock attempts, automatically wipe the device. As of Honeycomb, require the device be encrypted, and as of Ice Cream Sandwich, also disable the device's camera. So you can say, well, sure, if you want to be able to use this app, you won't be able to use your camera. That sort of thing. For, again, security/privacy reasons that enterprises have. Why would the user do this? Well, if they want to be able to get access to their corporate data. If they don't want to, if they say cancel here, they just don't, the app would, then choose what to do, but most of the apps would simply go and say, well, tough luck, you don't get to use it. You essentially app can ask the system to uninstall itself. That sort of thing. Go ahead. Sorry? This is not for monitoring other applications. This is really it really has to do with protecting data, right? So if the device, for example, is stolen, the enterprise can send, usually via something like C2DM, a code to this device and say, wipe yourself. Or if the user changes their password in, for example, the enterprise, this app, they can again, through some sort of a push mechanism, synchronize with this app, and this app can now change the password, the lock password of the device, right? Or they can say, well, we require your password be of a particular strength, and then they can enforce that policy on the device. So it's really about controlling access to the enterprise data that now makes its way on the device. That's really what this is for. Please.
You know how strong is the cleaning algorithm for the drivers?
So you mean in terms of how many times they wipe it and so on and so on? It's not something that's been very publicly discussed, and I've not seen it. I know Flash is a particularly problematic, essentially medium, because it has something called, wear leveling mechanism, whereby all the writes get distributed across the entire medium in order to kind of wear it down evenly. So when you think you're overwriting something, you're not really truly overwriting unless you override the entire medium. And when you do that, you have to override it several times. Right? So no, I don't know specifically how Android does it. I believe that it is essentially a full wipe. How good it is, how it compares, it's a good question. Okay? Rooting. So, finally we get to the juicy topic. So, rooting. So why rooting, right? Or why root? Well, access custom ROMs. It's one thing that people say when they want to root. Reuse old hardware. Remove offending system apps. Like how many of you actually use that NASCAR application on your Verizon phone? Get more speed if you want to get rid of some of the bloatware. Right? Get better looks. Cyanogen, is arguably better looking than some of the other mods out there. Like official mods. Because it's cool. Some people just like the idea of having a rooted device. Jailbroken devices are cool these days. Or you may actually not want to root your device, but there may be a rootkit that roots your device anyway. Okay. All this comes at a price. So let's talk about rooting. So how to? Okay. So typically we exploit so there's multiple ways, okay? One way is we exploit the weakness of the system or the existing ROM, right, of the system to gain root. That usually involves either exploiting the kernel and or exploiting something that runs with root privileges to give us essentially ability to run some code, our code, as root, and then thereby get root. Once we do that, one thing we do is usually we flash the recovery partition with a custom recovery, like Clockwork mod. We then download an alternate ROM when it's already rooted, most of the time, although we don't have to. Let's say Cyanogen. We then reboot in recovery into this new recovery, essentially partition, usually through some special key combination like power plus volume down or something like that. And then you boot into the ROM, and then ROM usually ends up having something called an SU file, which is essentially a binary that has a set UID bit enabled, and that binary talks to this application called superuser. So what's superuser? Superuser essentially So let me roll back. The way this works, the way you kind of get root on these rooted devices, is some app requests root by running SU. Okay? That binary goes and grabs the PID and the UID of that app, and it goes and checks in some local database, a SQL database, whether or not that app should in fact have root. Let's say that app has never been, prompted, or the user has never been prompted to grant root to that app. So what happens is that this SU fires the super user's activity via the AM command, which is some binary command that exists on all Android devices, and starts that activity. And that activity now comes up and says, hey user, do you want to grant such and such application root privileges? And you can say yes, once, always, or never. And so whatever selection you provide, that it gets stored into essentially the database. Your activity terminates, the SU command checks again the database and says, oh, so now I know what the user selected, and then essentially goes in, switches or sets the set UID bit, and off it goes. Now that app runs as root. Okay, that's how you essentially control who gets root once your device is rooted. Now, how do you get root in the first place? By the way, one thing I should mention is that some devices like Nexus S, Nexus 1, like Google devices, they are already unlocked, meaning that their bootloaders are unlocked. Or if they're not, you can type in something called fastboot OEM unlock, which usually wipes the data partition. And you're essentially, the bootloader now permits the fastboot to flash an entire new ROM directly onto the device. You don't actually need to exploit any weakness of the system. It was designed to allow you to install an alternate OS, just like your local PC at home is designed to, well, up until now, is designed to give you access to, to any OS. Okay? Now, getting root. So these are some of the exploits from the past. So exploit D is basically, that was an idea where Android, or this exploit, essentially took advantage of the weakness in the Android's init process, which is actually UEvenD on Android, which is what it does, or what it did, is that it allowed messages, these netlink kEvent UEvent messages that are normally supposed to come from the kernel anytime a new device is plugged into or discovered in a system, to this UEvenD. It allowed those messages, or didn't check that those messages in fact did come from the kernel, and that allowed our code to inject essentially arbitrary quote-unquote firmware to get executed inside of this init process, okay, or UEvenD. And essentially, we would fake a new device being connected to the system, and that device having some custom firmware that then needed to be executed in the root or with the root privileges, and that essentially gives us root. We then go and flash the recovery, and we're done. Okay, that's one way. Another one was the Rage Against the Cage exploit, which essentially took advantage of a weakness in the ADBD, which is this Android debug bridge daemon that essentially allows us to talk to ADB or talk ADB with the system. And what it did, essentially, it created thousands and thousands of ADB processes. And at any time an ADB process would run, it would normally run as root. And at the end of its execution, it would fork itself to essentially handle the connection or to handle the incoming request from the client. And what it would do just before it handles the connection of that request, it would actually change its effective user ID to the shell user. Well, the exploit here is that you would essentially exhaust all of the available processes in the system, so that last step, when you're supposed to essentially switch to a non-root user, would fail. So the last essentially command, this last ADBD command, or the last ADBD process that would run, would end up being running as root. It would be left running as root. And so then you'd get root. Okay? That required that you, as the end user, essentially do this willingly. The last exploit, though, this soft break / ginger break, is a little more sinister in that it actually takes advantage of a memory weakness or I should say buffer overrun weakness in the vol-D. And so the idea is, and this was, by the way, available in ginger break, so it may still be on some devices. So essentially, a specially crafted command would fool vol-D in executing arbitrary code as root. So that's essentially how you get root. Now, the danger with this last one is essentially that you get these rootkits. So the idea, if you download some malicious app from the net that you don't know, again, you can't vouch its authenticity, that app essentially can have this exploit built into it. It doesn't have to prompt you to run it. It can just run it itself, without shell privileges, and essentially it can get root itself without you knowing. The problem with rooting, okay? So the issues with rooting is all of these things like app isolation, permissions, data safeguards, even encryption, and this idea of device administration, all that falls apart when the device is rooted. When something runs with root privileges, essentially can circumvent all of these protections. Right? It can change your entire kernel. It can re-flash the entire device. So that's essentially the problem with rooting. While it's cool to have your device run as root, if you give a root to a malicious app, it's game over. Okay? You have to essentially re-flash your entire device and hope for the best that you can still recover your device essentially if you want to get it back into a clean state. So let me actually get through this. Sorry, I'll get to your question in the end. We have couple more minutes left, and then I know people will want to make it to the Romain Giesenschet's talk, so I want to finish this up and then we'll take questions afterwards. How about that? Okay. So some of the things Android is doing to prevent or to protect against rooting. So memory protections that are in place, like no execute to prevent code being executed. This is a hardware, essentially, feature that prevents code from being executed on the heap or on the stack. There's this pro-police that prevents or helps prevent buffer overruns or stack buffer overruns, safe I/O, reduce integer overflows. Some special, essentially, additions that Android adds in place, essentially, to help manage memory in a more sane way, so that they can avoid common, essentially, memory corruption issues that lead to buffer overrun weaknesses. Now, one problem though is on Android is this problem of shared libraries. So in Android, shared libraries don't take advantage, at least up until Ice Cream Sandwich, of this randomization that can be applied to them, called ASLR, which is address space layout randomization. They can move libraries anywhere in the memory. So if some code is able to get a buffer overrun or induce a buffer overrun, it becomes extremely hard for it to know where to jump to in order to execute itself, right? And so the way traditional operating systems deal with this is they essentially randomize how these libraries are loaded. On Android, these libraries are pre-linked, meaning their addresses are prefixed. So they can't be really randomized. And they're prefixed for performance reasons. So there are some, this is just a proposal on how to deal with this problem. And I suggest you read the PDF to get a full scope of it if you're interested. But while this was just a proposal back then, in Ice Cream Sandwich, this is finally reality. So in Ice Cream Sandwich, we're actually going to get true randomization of how our libraries are loaded, so it becomes extremely hard to take advantage of this, known addresses of the libraries. Let me just have a few more slides and we're done. SC Linux to Android. This is basically something that's, again, more of a research / pet project in a couple of IT shops. But essentially, if it were to become a reality, it would enable us to run almost everything in Android with not root privileges. So if any one of the Android subsystems were in fact compromised, the compromise would be more localized and it would not be able to, you would not get full root privileges. Unfortunately, SC Linux is not the most frugal thing on system resources, and it's not the easiest thing to set up. So it's something that Hitachi, for example, experimented with, but it has not become a reality on Android. But it's something that could, in fact, one day happen because it is based on Linux. Tab jacking. Let me mention this. Tab jacking basically on Android is something that you should be aware of as developers. So I'm assuming most of you know what toasts are on Android. Well, one of the things about toasts is that they can, in fact, cover the entire screen. So one of the things that malicious app developers can do is they can have an app that starts, let's say, a system setting that, say, changes some, I don't know, security setting on your system, and they launch it as an activity, and then they'll launch this game-like app that essentially covers the entire screen in a custom notification. And maybe their notification is like a game, actually bouncy ball going around. And the user is supposed to click on the ball. But what they don't know is that those clicks actually go right through the ball to the activity underneath. right? And that activity then takes those clicks, and if those clicks, for example, change the behavior of the underlying system, that can potentially lead to compromises. There is something called filter touches when obscured attribute that you can add to all your sensitive activities or UI widgets that essentially will prevent those touches from being registered by the underlying activity if there's a custom notification on top of it, which is what you should take advantage of. And I guess the last thing is with respect to best practices, do not or avoid apps that require root, because root can then lead to problems with your user's experience. If you are using encryption, be sure to know what you're doing. Otherwise, ask someone who does. Make sure your particular components are not exported, or if they are exported, which means they can be used by other components, make sure you test for the inputs and or use permissions, custom permissions. So where I'm going to skip these slides on the custom permissions, something that you should look into. It's well documented in Android, and you can see how to do this fairly easily if you again read the documentation. Also consider as users installing anti-malware applications, because they can scan apps being installed for signs of malicious content, whether by checking their package IDs or checking their signatures against some blacklist or whitelist, and based on that, give you hints on what should or should not be on your device. So if you wanted, you can build one yourself. Through Package Manager, you can get access to the installed apps, and through Package Manager, intents, you can get access to apps being installed, and you can then query them for whatever you want, a signature or names or whatever, and then basically decide whether or not they should be installed or uninstalled. These other concerns, security concerns, are minor. I think we should be wrapping up. We're out of time. I will be uploading this entire presentation to our server later on, and we'll make it available. Just go to this URL that I had initially, and this mrkn.co/nsec, and you'll get access to the latest slides as well as the presentation. Thank you.